Here we go. Okay, so Module 4. Module 4 is about velocity analysis. So we're going to be looking actually at Chapter 6. If we look at our learning plan here, you'll notice that we're going to be splitting this lecture or this module into two lectures, and we're going to be focusing on module or Chapter 6. So today we're going to get halfway through. We're going to do part 1. The next time we get together, we'll do part 2. And then we're going to be working out of this handout. For those who are virtual, make sure that you're printing that off because you will be handing the filled in handout out. If you don't have a printer right now, then you're going to have to like duplicate what's here, okay? So that you can hand it in by filling out all the information. So make sure that you're following along and paying attention to all the details. As we look at the rest here, you're going to notice that we have session recordings. So I'll be populating those with what we have this evening and the next time we get together. But you'll also notice that there are previous years out there. So feel free to take a look there if you need to peek ahead. And then our practice problems, if we click here, these are going to be what we're going to actively do in lecture today and the next time that we meet. So we're going to have one example out of the book, out of the chapter. So we'll do that early on here as we get into the Chapter 6. And then we're going to be filling out the handout that I was referring to earlier. So that's also located here. Additionally, you have a couple questions to answer, kind of the same ones that we've been looking at each one of the practice problems. And then finally, we have assignment number 4. There will be a large portion of this that you'll be able to do at the end of our lecture today. So I'll point those out after we kind of get through things so that if you did want to start looking ahead at starting that assignment, you would be ready for, like I said, a number of problems there. So let's take a peek at our learning plan. And I am going to click on the PowerPoint presentation here for what is Chapter 6 or velocity analysis. Additionally, what I'm going to do is I am going to get my camera going here so that I have that ready. Where are you guys? There we go. Okay, because we'll be kind of working out of both places. Okay. All right, velocity analysis, Chapter 6. So here in Chapter 6, we're going to be doing a number of things, but obviously it's going to focus on velocity. What really works out nice is that we're going to find out and really just kind of relearning that velocity is a vector. And really the reason that we did the vector work that we did in the previous module was to now apply it here in our Chapter 6 module 4. So we're gonna first define what linear, rotational, and relative velocities are and how we would use them in problems that we're going to be doing. We're gonna learn how to convert between and how linear and angular velocities are related. We're gonna apply what we call relative velocity graphically. So you're going to notice that there are sections in this chapter where they look at it, and again, in air quotes, analytically or using math, trig, mostly, to determine values, but we're going to stick with our graphical means. So that's what we're going to be focusing on here. And then we're also going to use that relative velocity method to determine what the velocities are, again, graphically, on not only points, but also different links that we're going to have in our mechanisms. So yeah. So in the beginning here, we talk about kind of introducing velocity. And really, when we're interested in velocity, especially on linkages, like the ones that we've been looking at here in kinematics, we usually want to know how fast are certain points on a link traveling, okay? It might be endpoints, it might be the link itself, but how fast is it going, okay? So we've got things that are moving. So the determination of the velocity on a link is really the purpose of this particular chapter, okay? And we're going to be using relative velocity when we start kind of, if you would, stringing together different links to make a mechanism, because then as we move one mechanism and we're 2 or 3 links down, the motion is going to be relative to what's going on, early on in the motion cycle. So linear velocity should be very familiar to you guys. I think I heard earlier, a lot of you are taking, or some of you are taking your physics class right now, right? So this is Classic physics. Okay, it's an application of physics. So we'll do a review here, but this should all be exactly that, a review. So linear velocity, which uses the variable v, is going to be a straight line displacement of a point per unit of time. Okay, the equation that they use here in the book, but we'll see different variations of it, is v for velocity is equal to, they're using r for distance or displacement, divided by time. Many times you see that displacement as either s variable or as a lowercase d, okay, which are, d is going to be usually what I use just because that's what I'm used to. So it's going to be distance that's covered divided by the amount of time it takes to cover that distance, okay? So when we look at units for velocity, they are going to be exactly that, distance divided by time. So feet per second, miles per hour, inches per second, meters per minute, you know, whatever it might be appropriate for the application that you have, whatever the distance is, and then whatever the time is. Now, velocity, as I'm sure you have run across, and we did mention it the previous unit, is going to be represented using a vector, or we say it's a vector quantity, which means that we need two things to fully define it. We need its magnitude, and that's going to be whatever it is in feet per minute, miles per hour, you know, the magnitude of the velocity, or what we refer to a lot of time as the speed, okay? But then we also need to know what its direction is, and that's what's going to give us the fully defined vector for velocity, okay? Now, talking first about rectilinear motion. This is when we have motion that goes in a straight line, okay? This is the classic v is equal to distance divided by time. So we're going to look at our very first example, which is on page 124, example 6.1 in your book, okay? So if you want to open up at the very top of that page, we're going to see this first example. So I'm going to scooch this down up here. Okay. So up at the top of the page here, it says crates on a conveyor shown. So here's the conveyor right here, and here's the crate. Move towards the left at a constant rate. Okay, so as you know in physics, that just means that it's moving constantly. It's not accelerating, it's not decelerating, it's just moving along. Okay, and it's moving at a rate that takes 40 seconds for that crate to traverse or cover 25 feet on that conveyor. They want us to determine what is the linear velocity of that crate, okay, on that conveyor, okay? So using the equation that we just learned, okay, so again, this is going to be your first practice problem. So you're going to want to just kind of label this is example 6.1, okay? To calculate velocity or how fast something is going, right? Velocity is going to be equal to, and I'm going to kind of use my normal because you're going to see me do this throughout. It's going to be equal to distance divided by time. Now, as you probably, I think all of you probably had me for technical statics, right? So as you know, the way that I like things formatted, or need you guys to format them, or require you guys to format, is that if we have an equation, we want to put it in variable form first, okay? And then what we're going to do is we're going to add in numbers with units as we go along, then cancel out our units, and then our final answer with the appropriate final units, okay? Now, as we look at this, just as a kind of a review, just to make sure we know what things are, v is equal to velocity, right? Okay. D is going to be equal to distance, okay? It's going to be how much distance we cover. And then T is going to be equal to the time that it takes to cover that distance, okay? Now, as we look at our problem, it's telling me, as we look at distance, all right, it says it's going to traverse 25 feet. When I'm looking at distance, I'm looking for, so it might not say the distance that we're going to use for this equation is 25 feet. It's usually in the form of, here's your problem in kind of story form. And then we have to pick out what the appropriate things are. So if a distance is something we're looking for, we're expecting those units to be inches, feet, meters, centimeters, whatever they might be. And you'll notice here that it says to traverse 25 feet. So 25 feet is going to be our distance, okay? So D is going to be 25 feet. So we can say velocity is equal to 25 feet, okay? And we're putting our units right next to it, okay? Do not just put 25 on top here and say, well, you know, she'll know what units those are. No, no, no. You have to put the units in every phase of the problem, okay? Divided by the time that it takes to go 25 feet, it says 40 seconds. So we're going to put 40 underneath and then seconds, okay? So now my velocity, I'm going to take 25 divided by 40. What do we get for a number here?
0.625.
0.625, that sounds correct. So 0.625. And then our units are going to be what?
Feet per second.
Feet per second. So we're going to put it in here as feet per second. Okay. Now, if we look at the answer, they have this written out here as well. Now, you'll notice that they have deltas or triangles in front of the distance value. They use R, and in front of the time. All that means is that was the amount of distance that was covered in this amount of time. Okay, so whether you put the delta or not, it really doesn't matter because it's the amount of distance and the amount of time. So that's okay. So they've got the 25 feet over 40 seconds, just like we had, and then they have 0.625 feet per second. Now, in parentheses, they put this 12 inches over 1 foot. Why did they do that? It's just a conversion, right? It's just a conversion. Now, in the problem, they did not state convert to inches per second, okay? So that's like an extra thing that they did. So you can leave if there's no directions to change it to new units. You could stop right here and this would be your final answer, okay? Remember, your final answer has to be labeled with the variable. Do not just put a box around 0.625 feet per second. You have to tell me what it is. V is equal to, okay, 0.625 feet per second. Make sense? If you do this and put a box around it, you get points off. Okay, so formatting, I want you to answer the question. It's asking us, what is the velocity, right, of that package? So you have to say V is equal to, and what the number is, okay, with the units. And also the units have to be up here. If we end up canceling and such, then we'll have to check the remaining units to be sure that they're in the correct units that we need. So when we look at velocity, because it is in the equation form of distance divided by time, our units are going to be exactly that too. Distance on top, in this case, feet, and then over time or per second, per unit of time, which is seconds. So velocity is feet per second. What are other units that we could see potentially for velocity? What did you say? Meters per second. Yep. And I'll open up the chat box. So for those who are virtual, you can chime in as well. In general, miles per hour would be units for velocity. Yes. What else?
Millimeters per second.
Millimeters per second. Yes. So any distance over time. Inches per second, millimeters per second, kilometers per hour, miles per hour. Correct. Those are all units for velocity. Units for distance. What are those? I know it's as easy as feet, inches, millimeters, meters, all those types of things. And then what about for time? Seconds, minutes. Did you say hours? Absolutely. So what I'm trying to get at is you're going to want to get yourself familiar with what are the units I'm trying to achieve so that in the end, when your units reconcile, whether it's combining or in this case, they combine, they don't cancel, you make sure that you have the correct format of units so that it gives you that clarity, that confidence that you set everything up correctly. Does that make sense to everybody? Okay, so units are going to be a big deal here. So make sure that you're showing them in all phases of the problem and that you end up with the appropriate units in the end. Units do not magically appear. So if you do 25 over 40 and then magically feet per second appear, points off. Okay, I want you to see that they actually occur. Okay, and then like I said, if you're not getting the right units, the best question you can ask me is, can you show me how to get the units here because I'm not getting them quite right? Perfect. I'll spend all day on that. Okay. So make sure you have everything formatted in this example like this because this is going to be your first one that you're going to hand in. Okay. Let's go back to our handout. Where's my, okay. On the next PowerPoint presentation here, it says now we're going to go to that handout that was provided in the module. Okay. So for those who are in class, everybody's got the handout here, right? Okay. For those who are virtual, hopefully you were able to print it off. Okay. It's in module 4, right in the learning plan. So it's the handout. It's a PDF. Okay. So the reason I think it's advantageous to print it out is because there are, as we look further in the handout, there are blanks that we'll be filling in. Otherwise, you're going to have to recreate it if you would, when you hand it in for the practice problems, because you'll still be responsible for all of those items. So at the top here, this first page is kind of like a review, if you would, or kind of bringing together the concepts and the relationships. So first of all, linear velocity, which we just covered. Velocity is going to be equal to distance divided by time. So in this case, S is being used for the variable. But like I said, this can also be D over T, or that R over T that you're going to see in the book. Okay. So things that are going to have linear velocity are going to be things like we saw earlier. A conveyor belt, car moving down the road, person walking, a distance. That's going to be a linear velocity. How much distance was covered in how much time? Okay. So D divided by T. Now, when we start looking at items that are rotating, so this is straight line, linear, rectilinear or linear velocity, and that's always going to be the letter V. When we start looking at things that are rotating, okay, now we have a new type of velocity, and we call that angular velocity or rotational velocity, kind of the same thing, but two different words for it. So angular velocity is going to be, as we look at, for instance, a single link that rotates about a fixed center. As it rotates, we're going to describe that motion as angular velocity. And the units for angular velocity are going to take one of two forms, either revolutions per minute or radians per second. Okay, and there's going to be certain times when we use each. Okay, so angular velocity is going to have the variable W, okay, or lowercase omega. Okay, lowercase omega. Now, let's kind of look at what we have going on here. It looks kind of familiar. You're going to notice down here, this is the symbol that we use for a frame, or to symbol, if you would, a point that isn't moving. And that point happens to have a link connected to it, okay? Now, because that link is connected to this fixed point, it can move only in a circular path with its fixed center at A or at the frame, right? Okay. Now, as this moves around, as we stated just now, that link is going to have angular velocity. And we are going to give it a number. We're going to say, okay, it's rotating at an angular velocity or rotational speed of 100 RPMs, okay, or 10 RPMs, or 1500 RPMs. So it can go very fast or it can go slower, okay? But telling us how many RPMs, which is revolutions per minute, it gives us how many times this is going to go around in 60 seconds or in 1 minute. We can kind of get a feel for that. We can kind of relate to that unit of measure, right? So 1700 RPMs, revolutions per minute, that's going to be moving pretty fast. That's like motor RPM, okay? But something maybe like 10 revolutions per minute might be like merry-go-round at the park, okay? So any single link, for instance, can have rotational motion as long as it has a fixed center that it's going to revolve around, okay? Now, we have points along that link. You'll notice that I have marked X, Y, and Z. And in each one of those points, you're going to notice that there is a velocity vector. So a given point on a link is not only going to share the same rotational speed as that entire link. So everything on that link has that same rotational speed, but a single point will also have straight line velocity. Okay, or we say it's the straight line velocity component of the motion for that point. You maybe heard it like that. Okay, so as we look at point X, notice that it has a velocity at X, Y velocity at Y, and Z velocity at Z. Okay, now something about each one of those velocities. Number one, each one of them is shown as a vector. Okay, so it's a line with an arrowhead. Now, a vector, as we know, is fully defined through magnitude. So we would calculate its magnitude, and we'll find out how to do that here. That's this relationship. We'll use it in a little bit. So we can calculate the magnitude, but we also have to know direction. And that direction is going to be determined by, number one, the direction of rotation of that rotating link. So this velocity for each one of these points on that link that is rotating in a clockwise direction, those straight line velocities have to be consistent with that rotation. So you'll notice here that at this moment in time, we would stop this instantly, and each one of these points would fall off the link, okay? They would continue not going in a circle, but they would continue going in a straight line fashion, and in each case down and to the right. Okay, right? If we stop and we're going in a clockwise direction, we're not going to stop and they're going to fly off going up and to the left, right? They're going to go down and to the right. So that's the straight line component. So that gives us one portion of the direction. The other portion of the direction is going to come from its relationship to its line back to its center of rotation, or its radius back to the center of rotation. So for instance, for point Z, if I take a line and I draw it straight back to the center of rotation, which is A, this vector is going to be perpendicular. That's that perpendicular symbol that we see here to that line back to its center of rotation, okay? Or perpendicular to its radius of rotation. You'll notice the same thing for Y. It's perpendicular to its line back to its center of rotation, or the radius. And then the same thing for X, okay? And then lastly, you'll notice that the relationship of the lengths of each one of those vectors, okay, is going to be smaller velocity as we're closer to the center of rotation, larger velocities as we get further away. And this has to do with that radius of rotation, how far away we are. Okay, so we'll talk about that in a little bit. So any questions right now as we look here? You'll notice some familiar things. As we said earlier, this is a frame member signifying that the center of rotation is not moving. Okay, whether that is physically, going to be attached the way that we see it, as we know, this is just representing, it's a symbol for something that isn't moving. Okay, so the design of this is not what we're interested in. We're just interested in saying A is not moving. Okay, and because of that, it's going to be considered a frame member. So that's why it's called number one. And then as we look at the actual link itself, because it's connected to the frame and we just have these two items, this is going to be link number two. Okay, link number two. So that's why we call this the angular velocity of link number two. That's going to coincide and go along with whatever we label the link as. Does that make sense? Okay. All right. So link 2 rotates at an angular velocity of W2. So that's going to be our symbol for that. We have points X, Y, and Z each have a linear velocity, Vx, Vy, and Vz. The direction of those linear velocities are pointed in a straight line in the direction of rotation and always perpendicular to the radius of rotation, which we just talked about. And then here is the relationship of straight line velocity V, angular velocity W, and the distance that each one of these points is away from the center of rotation, R. Okay, so V is going to be equal to that straight line velocity, angular velocity, and radius. So our radius of rotation, for instance, for point X is going to be Rx from the center of rotation to that point. Then you're going to notice that our Ry is going to be from the center of rotation to point Y. And then our Rz is going to be from the center of rotation all the way out to Z. Okay. Now, the reason I want to point that out and kind of show that is because now that starts to make clear why our velocities are getting greater as they go further away from that center of rotation. Okay, so you'll notice here that Rx is the smallest radius, and you'll notice that our Vx is the smallest length vector. So V is going to have the same W for each one of these because they all are on the same length, but the thing that varies is going to be R. So as I get further away, those velocities get greater because our radius gets larger. Does that make sense to everybody? Okay. How many people are bored by this and have heard this all and understand these relationships? Raise your hand. Oh, maybe not. Okay, so it's a good review. Okay, so, but you've heard this before, right? Even if it's not top of mind, okay? So these are the things. All right, let's turn the page. Let's turn the page. Now, let's talk a little bit about units. So straight line velocity, we've already kind of talked about this in that example. When we have straight line velocity V, what are the units that we would expect? And we want to fill this in, right? Meters per second, what's another one? Feet per second, what's another one? Kilometers per hour, sure. What else? No, none else. None else. Miles per hour, yes. And then Drew had inches per second. I'm going to use inches per second for this one, okay? But yes, it would be any units of distance divided by the units of time, but we're going to use inches per second right now. Now, a radius or a distance, what are units for distance that we could use? Inches, yep, I'm going to put inches in here. What other ones? Meters, what else? Feet, yes. Kilometers, absolutely. Miles, right? Yes, 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 all of those. So whatever your distance or your radius. So in this case, our radius is going to be that distance from the center of rotation to whatever point that we're looking at. That would be the units. Angular velocity, W. Now this one might be a little new, okay? So angular velocity is going to be revolutions per minute, okay? That's it. And we're going to look at another one, but really kind of the same. It's derived from, okay? Now, if we look at that equation earlier, and let's say we want to rearrange this relationship of V is equal to W times R, or straight line velocity is equal to angular velocity times the radius of rotation, and we want to solve for angular velocity. We're simply going to algebraically solve for W here so that we take our R and we divide it on both sides. So we come up with this relationship right here. So it's really the same equation as V is equal to WR. It's just rearranged to be W is equal to V over R. Do you guys see that? Okay. Now, when we do that, and if we use the units from above here, so let's say we use inches per second for velocity, okay, up on the top. All right. Now, something I'm going to tell you that you are going to do from here on out, whenever you see any units that are in, if you would, fractional form, you know, like we see here, inches per second, revolutions per minute, we are going to show them in what I call the up-down format, not the slash, okay? Do not write any units inches per second, okay? We're not doing that anymore. The reason being is when we do our cancellation here, we've got to see it actually happen. And you can say, well, Kelly, I can see it. Well, that's nice. You're going to make mistakes when you do it like that. Okay, I've seen it over and over again. So you have to do it this way. So for your homework and when you hand in, make sure that all of your units that are in that, if you would, fraction form are in up, down, numerator, denominator, not with a slash. Okay. On the bottom, our radius, if we use the units that we had up here, are in inches, right? Now, if I look at these units, this is where it's going to be important that we put our units in all phases of the problem, because now you're going to cancel out and you're going to see what did I end up with. So here in the numerator, I've got inches in the numerator of the numerator. Those are going to cancel with the units in the denominator. So now what I have is I have nothing per second, okay? But when I'm in a rotational mode of motion, it magically appears to be radians per second. Do you guys remember that from physics? Yeah, yeah. What was that? They do magically appear. They're like Lucky Charms. Did you know that? They're exactly like Lucky Charms. They may not be magically delicious, but they do magically appear and magically disappear too. They do. They do. So, yeah. All right. So that's the way that you can remember it. But here, as you'll see, if I do my units correctly and they cancel out and I end up with that W and I end up with radians per second, I know I set it up correctly. I know what I set up correctly. Now, why is this important? Because as you'll see here, remember we had W, angular velocity is W. We had revolutions per minute. And then in this equation, when we put the velocity in the radius in, we ended up with radians per second because of the cancellation. So there are, if you would, 2 units for angular velocity, but we're going to see them being used at different times. So many times your angular velocity is going to be given to you in RPM, and that's going to be because that's the way that we specify angular velocity in the world. So if you go to the motor store and say, Mr. Motor, or I don't know, whoever is at the desk of the motor store, I need a motor and I need it to, be in 1000 RPMs. They're going to go and they're going to grab it for you and they're going to get it for you. Okay. But if you say, I need a motor that runs at 15.7 radians per second, they're going to be like, yeah, that's nice. What is that value in revolutions per minute? Okay. Also, when you report out, if I have a problem for you and it says, what is the angular velocity of blah, 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 that's one of the answers you're getting, you're not leaving it in radians per second. You're always going to convert it to RPMs. And that's going to be the practice that we do down here. So if we get something in RPMs and we have to convert it to radians per second, we got to know how to do that. So down here, we're going to use what we call the ratio method of unit conversions. Okay. Yes, there are unit converters out there that you can look up online where it says just multiply by this number to go from revolutions per minute to radians per second. You aren't going to use those. Okay. I won't accept that. What you are going to do is you're going to manually write it out so that you can see that it is correct. Because those calculators, you might be like, oh, I have all the confidence in the world, but I don't know. You got to make sure that your units are correct. This will always work, okay? So what we're going to do is, as you can see here, we're going to start 500 RPMs is equal to how many radians per second? We need to expand out the RPMs. RPMs are revolutions per minute, okay? That's what the RPM means. So that means we're going to have revolutions on top. The per is going to be our division sign, and then minutes are going to go on the bottom. So you have to expand this out. You cannot write this as 500 RPM on top and do the conversion. Not going to happen. Okay. Revolutions on top and then per minute. Now with that, we also have 500 is over 1, if you would. And if you think about it, it's 500 revolutions per 1 minute. Okay. That's what we really have. But we usually don't put the 1 in the front here, but it is. So 500 in revolutions are, I like to say, on the top, minutes are on the bottom. So if I want to get this to be radians on the top, that means I have to get my revolutions into radians. How many radians are in 1 revolution? Do you guys know? Do you remember the number? Yes, 2 pi radians equal 1 revolution. Okay. So if revolutions are on top here, what I'm going to do is I'm going to put revolutions down below. and radians on top. And I'm going to do that because I'm going to multiply across my top and I'm going to divide by the bottom. So revolutions cancels. Do you see that? So now I got to put my numbers in there. If I know that I have 2 pi radians, that's going to go on top because radians are up there, and then 1 revolution underneath. So right here between my lines, my vertical lines or my brackets, this is the conversion in what we call ratio form. Okay. So now when I multiply across the top, divide by the bottoms, revolutions cancels out. And the units that aren't canceled out yet are radians per minute. Do you see that? I need to get into radians per second. So now that means since minutes are on the bottom here, I'm going to say, all right, minute on the top, that's going to cancel, and I need to get into seconds. How many seconds are in a minute? 60. So I'm going to put 60 on the bottom and 1 on the top. This is my conversion in ratio form. I have to put the minutes on top because they're in the bottom in the original units. Now, minutes are going to cancel. So now if I look at the units that are not canceled, I have radians per second. And that's what I need in the end here. Does that make sense? So now I'm going to take my 500, I'm going to go across the top. I'm going to multiply it by 2, multiply by pi. Then I'm going to divide by 60. What do I get for a number here? Everybody should be doing it. I got, there's a 52.36. Is that, anybody else get that number? Whoopsie, 36.
Yep, I got the same thing.
Same thing. Thank you, Nicholas. Awesome. Okay. How many have done this method before for unit conversions? Okay. You're going to love it. Even if you haven't done it before, it like clarifies it all. Too often when people don't understand how to use or don't do them often or don't understand how to do them, unit conversions seem, like, I don't want to do it. I'm just going to add them at the end. Okay. But they are your confidence that you set things up correctly. 95% of a problem, all of a problem is really set up. And if you end up with the correct units in the end, you're going to know that you had it set up correctly. Okay. When I was at the other college I was at, I taught physics as well. And I taught physics for not only my program area, mechanical design, but I taught physics for electronics, electromechs, what else? Nuclear, a couple different program areas that required it. And the other program areas besides me, they would inevitably, especially electronics guys, they would be like, well, our other instructors don't make us do units. Okay. So why should we have to do them here? I said, well, I'm your instructor here. And you need to do it. If you don't, that's okay. You don't have to do it, but you'll get points off. So they started doing it and they weren't very happy with me at all. They were, and I was kind of being snarky back, like, whatever, you'll get it. As we got into the semester, they would groan at the beginning, but then they started telling me, and this was every single year, at least one person, and then I would have a couple other people chime in, and they would say that they started doing unit conversions in their other classes that weren't with me. And all of a sudden, everything started making more sense. And they started like getting why the units were coming out or why it wasn't correct when they did it. Okay. So apply this in other areas. If you even know the units of something, it's easy for you to kind of derive backwards what the equation might be. Okay. When you think of velocity, you think of feet per second. Well, then that must mean that the distance is on top and time is on the bottom. Does that make sense? So I know that's an easy example, but just know that even though some of the stuff we're doing right now, you might be like, I could just do it in one, thing and have it done. Writing it out is so advantageous, not only in here, but in other courses that you're going to come upon. Machine design elements later on, you're going to have to do this type of work. Okay. Make sure that you get the right stuff. So this is a really foolproof method of doing that. All right. So this was RPMs to radians per second. Now we're going to go radians per second to RPMs. So we're going to start with 10 radians per second. Okay. And now I need to get to revolutions per minute. So I expanded out RPMs over here. So in my first box here, I always like to start with, it really doesn't matter if you start with the radians or the seconds. I always start with the top first. So I know that I'm going to put radians on the bottom, revolutions on the top. And I know that there are 2 pi radians in 1 revolution, right? 2 pi radians in 1 revolution. So that means my radians are going to cancel, and now I'm in revolutions per second. Seconds are in the bottom. I need to get it into minutes. So seconds are going to go up top here. Minutes are going to go in the bottom. I know that there are 60 seconds in 1 minute. Okay. And that means my seconds are going to cancel top to bottom. And now the only thing that's uncanceled is revolutions per minute. If you're ever wondering like which side to put this on, top or bottom, look at where it is. So if seconds are in the bottom in your original units, it's going to go on the top in your conversion. If radians are on the top in your original units, they're going to go in the bottom in your conversion area. Now, I use the vertical lines for conversions to show that they're offset from, for instance, if you use parentheses, a lot of time that's going to be for variables in an equation, okay? So I use the vertical lines to just kind of show this section is unit conversions as opposed to like variables in an equation. The book doesn't use the vertical lines. It's just a way that I learned it early on, and I've just kind of continued to do that. So now to solve for the number here, it's going to be 10 times 1 times 60 divided by 2 divided by pi. What's my number here? 95.5. Anybody else get that number?
Yep.
Awesome. Oh, there you go. Thank you. Thank you, Alex, online. Perfect. So questions. All right. Let's practice. Got a couple examples here. So our first example, we want to determine the straight line velocity of point B as line, actually, it should say link, as link 2, not line, link 2, okay, rotates at 100 RPM counterclockwise, okay, as link 2 rotates at 100 RPMs counterclockwise. So as we see here, we can see that we have kind of just a standard frame, right? And a link, number 2. We have the points, the endpoints, or the pin connections identified here as A and B. And we know that our link is 10 inches long based on this, okay? So some information they give us in the problem is that the link rotates at 100 RPMs counterclockwise. So we're going to show about the center of rotation like an arc, okay? And we're going to show it pointing in a counterclockwise direction. And we're going to label it W2 is equal to 100 RPMs, okay? Now, how do I know it's W2? Well, it says that the link, and we have the link identified as number 2, is rotating counterclockwise, and angular speed is going to be a variable of lowercase omega or lowercase omega or W. I say W2 all the time. Okay. Now we want to determine the straight line velocity of point B. Now, as we remember, if we go back to our first page, we saw that points along a link are going to not only have the same angular velocity as the link, but they're also going to have a straight line velocity component, right? So what we want to do is we want to add the V to point B, straight line velocity component. And most often you're interested in that point that is at the end of the link because that's your, if you would, worst case scenario. That's going to be where the highest velocity is going to be, okay? So what we're going to do now is we're going to draw that velocity vector. So it's going to be a straight line velocity. It's going to be perpendicular to the radius of rotation, and it's going to be in the direction of rotation. So if this is my link right here, that means that my velocity component, or my velocity, is going to be perpendicular to that link, 90 degrees, and it is going to point in the direction of rotation. So I have it going up and to the left, and this is going to be velocity B. So think of it as if this is rotating, rotating, rotating around, and I suddenly stop, point B is going to continue its motion in a straight line. In this case, if we stop right at that instant, up and to the left, okay? Because that's the direction. It's going in the direction of rotation, perpendicular to the radius of rotation, okay? So we want to determine what that VB is, okay? So determine the straight line velocity. So that is VB the velocity of point B, okay? Now, equation. So we're rotating. So we are going to be using this equation right here from the relationship of straight line velocity to angular velocity and its distance away from its center of rotation. So our equation is going to be velocity of B, because we're looking at specifically point B, is going to be equal to angular velocity times radius. Now, because point B is on the end of link number 2, the angular velocity we're going to use is going to be W2. Okay. And then the radius, the distance, is going to be from the center of rotation out to that point. This is going to equal R sub B. So we're going to put a B in back of this because it's the radius to point B. Okay. So now we'll fill in our numbers. We'll say, okay, 100. Now remember, revolutions per minute. We have to show it in its up-down format. So this is going to be 100 revolutions per minute. That's our W2, right? And then we're going to take our radius of B. That's going to be 10 inches. Okay. So when we multiply this out, our velocity B is going to be 1,000, right? 100 times 10. And it's going to be revolution inches per minute. Box around that, ready to go, right? Who thinks that this looks good? Got my units in there. I'm all set. Jesse and Tyler, you guys are like back row. Don't think so. Jesse would rather have it in inches per second. Anybody else rather have it in inches per second? Jacob, you're like, no, it's good. It's good. Easy. I could do that one in my head. I'm good. We're back here. Let's look. On page 2, we said velocity needs to be in inches per second, you know, some distance over time, right? That revolutions are in there. You know, the inches are fine. The minutes are fine. It's the revolutions. Let's look back. Do you remember that little statement on the second page? Many times W is given in RPM, right? You need to convert it to radians per second to use it in the equation. We need to get it in radians per second, right? And then they'll magically disappear when we do the multiplication. So we cannot, and this was on purpose. I did this on purpose. We're going to erase these 2 lines here because we cannot use revolutions per minute in this equation. Okay. In and out of this equation, if we're solving for W out of this equation, we're going to get radians per second. If we're using it in the equation, we've got to put it in radians per second. We can't use RPMs. So I'm going to, right over here on the right-hand side, we're going to say, okay, W2 is equal to 100 revolutions per minute. And now we're going to convert into radians per second. So starting with my revolutions on top here, I'm going to put revolutions on the bottom, radians on top, right? Because I need to get radians per second. So I know that there's 1 revolution is equal to 2 pi radians, and my revolutions cancel here. Okay. Now I'm in radians per minute. I need to get to radians per second. So I'm going to put minutes on top, seconds on the bottom. I know that there's 60 seconds in 1 minute. Minutes cancel top to bottom. I now have radians per second. So my W2, I'll take 100 times 2 times pi and divide by 60. What do I get for my W2 now? 10.47. And what are my units? Radians per second. Yes. And remember, up, down, don't slash this because now we're going to put it over on the other side and this is going to go here, not the revolutions per minute. So this is going to be 10.47 radians per second. Okay. And then my radius is going to be 10 inches. David, do you have a question?
Yeah. When we get Just so where's we saw that. Is there a case where we would want to keep it as an exact value, so like leave it as 3 1/3 pi?
No.
Or need it somewhere else. You're always just gonna,
Yeah. So the question is, do we want to use 3 1/3 pi?
or at least keep it somewhere in case.
Nah.
Further.
No, what we're using most often isn't that critical. So yeah, if you know that it's going to be that critical and you want to hold the pi in there, fine. But honestly, for what we're doing is it works out 2, 3 decimal places. 3 is always pretty good.
You always leave it as the exact value. So, curious.
Yeah, no, we'll be fine. I always pull them out or put them in their decimal form. But good question. So now we have our angular velocity in radians per second. We're going to multiply by inches here, right? So our velocity at B is going to be equal to 104.7 radians times inches. What happens? Radians are going to magically disappear, right? So it's going to be inches on top divided by seconds. So whenever radians is multiplied by something else, the something else takes over, right? If there's nothing left, then and we're in a rotational atmosphere, then radians magically appears, okay? So 104.7 inches per second is the straight line velocity, VB, at point B when we have link number 2 rotating at 100 RPMs. So good. Questions? Okay. Example number 2. Oh, can I call it R2 instead of link 2 or instead of RB? No, because we're going, Tim, good question. Yes, in this case, this is the length of link number 2, but we are going to point B, and point B is at the end. So you need to call this RB. Yeah, because we could have a point here that could be another letter, and it would be then RC or something like that. Okay. Yeah. The numbers are for the links, and we're going to a point or two. This, in this case, it's a joint. Those are going to be the letters. Yep. Thank you. Good question. All right. Example number 2. We're going to use kind of a similar looking frame and a link. Okay. Endpoints are the same letters, but this time we're given 250 inches per second on a line with an arrow pointing down and to the right, and we want to determine the angular velocity of link number 2. Now, angular velocity of link number 2, that means we want to find W2, right? We want to find what is W2. And we need to find it in revolutions per minute, or you can write it as RPMs, revolutions per minute or RPMs. Okay. Now, if I look at that 250 inches per second, what variable is that? What would we call this? We got to call it something.
VB.
VB? Anyone else? I'm seeing nods. People in the room like it. What about virtually? Would we call this VB?
I'd say yeah.
Yeah, you're correct. So we're gonna go like this. VB is equal to, right? We can see that it's positioned, it's shown perpendicular to the radius of rotation. Okay. Now, you'll notice that we need to find W2. To fully define W2, we not only have to find its magnitude, which we will, we also have to show its direction. And we can show its direction on here right now. Go ahead and put on a direction that you believe W2 is going. So draw an arc, okay? Label it W2 and show an arrowhead either on the left-hand side or on the right-hand side of your arc. Now, which way did you show it? Did you show it going clockwise or counterclockwise? I've got clockwise, clockwise. What else?
Clockwise.
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 Clockwise. Yep, virtually clockwise. All right, tell me why. How do we know? Dylan says vector B is pointing this way. So if I put my finger on the point of rotation, right? And I pull in the direction of the 250, yeah, the arrow is already pointing in that direction. Absolutely. And it's going to pull that link in that direction. So the straight line velocity and the angular velocity are going to go, if you would, in the same direction, right? Good. But we don't know everything about W2 yet. We have to find its magnitude, right? So if we look back at this relationship, V is equal to W times R. We know what W is, right, of a point on that link, the VB. I'm sorry, we know what V is. We know what the radius is because we know how long that link is, and that point is on the end of it, right? So this is going to be our RB, right? RB. So we need to find W, okay? So rearranging that equation, W2 is going to be equal to VB divided by RB, correct? Double check my algebra. All right. So now, if you put in the values here with the units, see what you get. Go ahead and do it, and then we'll compare. So put VB on the top, RB on the bottom, put your units in, cancel, see what you get. So if I look above, my VB is 250 inches per second. Remember, up, down, no slashes. And then divided by RB, which is 15 inches. My inches cancel top to bottom, right? So my W2, what's my number? 250 divided by 15, what's my number?
16.6.
16.6. Okay, units. What are my units? It's nothing per second, but it actually is what? Radians per second. They do what? Say it. They magically appear. I know, it's even fun to say it, isn't it? So these are going to be radians per second. Now, can I leave it in this form? Am I going to go to the motor store? I need to get a motor to turn this. And if I ask the motor store person, the motor store and salesman, could you give me a motor that goes 16.6 radians per second, please? They're going to be like, no, but I can get you one in RPMs. What do you want that in RPMs? So let's convert it to RPMs, okay? Your final answers for angular velocities always have to be in RPMs. You're going to get them out of this equation in radians per second, but you're going to convert it to RPMs each and every time, okay? When it's a final answer. So here, I know that I have 2 pi radians in 1 revolution. Radians cancel. And then I know that there are 60 seconds in 1 minute. Seconds cancel. So my W2, what do we get? 16.6 times 60 divided by 2 divided by pi.
Yeah.
And that's going to be RPMs, right? You can put RPMs at the end. Did everybody else get 158.52? Yep. Confirmed. I don't have it in front of me. 159.15. So 16.6 times 1 times 60 divided by 2 divided by pi. 159.2. 150. So if you take 16.6, don't have the extras, just 16.6 times 60 divided by 2 divided by pi, what do we get? 158.52? Okay. Same thing. Okay. If you hold this and you keep these and then you continue, it might be that 159. Is that what's happening? Okay. All right. Yeah, I'm just going to stick with what's here. So, all right. So, box around this. Okay. And again, this is an angular velocity. You would not stop at the radians per second. You want to then convert and you want to report, if you would, your final answer in RPMs. Okay. So for right now, that's as far as we're going to go. We're going to take our break. And in 15 minutes, we'll come back and we'll continue on in our handout. So I'm going to stop the recording.